Okay, let me just do a mic check. Test. Oh, I am live. We are live. Welcome to another Tech Day. With me, the Duke Dev. So where have I stopped last time? I think here. Okay, so this is a simple support vector machine classifier. We are using the iris dataset, and it's only a small snippet of code, but it does multiple things. All right, I have NumPy, I have a load iris. Wait, this is located in scikit-learn in the default library. Where's the iris CSV file located? That's something that really interests me. I have these feature names, and I just return everything. I return a bunch. What's bunch? It's a type. It's a dictionary type. New dictionary initialized from a mappings object pairs new dictionary. All right. I didn't know that load iris is a scikit-learn method. I didn't know this. Interesting. Interesting. Then I also import make pipeline. This is a utility function to build machine learning pipeline, because I need to chain pre-processing, I need to change modeling steps. It makes the code cleaner, it makes the code less error prone actually. All right. This will actually create an object behind the scenes that runs each step in sequence. It's gonna run one step, then another. I have also the standard scaler here. So the standard scaler will help us, because many models will work better when input features are on the same scale. Right, so you have the scaler as well. Linear SVC, it imports a linear support vector classifier. We need it because we are training a binary classifier to recognize if a flower is a iris virginica or not. And behind the scenes, I would like to implement, okay, let me just write something for the future. Implement, understand, maybe the standard scaler. Standard scaler or linear SVC. All right. Then we load our data. Then we load our data, and what's this? What is this returning? Is this? It's a tuple. But it should be a data frame. I think this is a data frame. We need iris because we want to access individual columns. In this case, I want to pull on only these two columns. I think I have more than this. Oh shit, it's gonna fail. No, it didn't fail, but I need to run also all the cells above. Every time when I reopen Visual Studio Code, I need to run every cell above. In this case, it just passed. I assume because this cell is more or less self-contained, it doesn't depend on anything above. But if I wanted, for example, to reference X outliers here, it wouldn't work. It would work by default. So that's why I had to run all the cells above. Where was I? Okay, so this is data. This is the ID. We have all these sepal lengths, sepal widths, petal length, petal widths. Okay. I don't need this anymore. I just did this for a visual reference. All right. Values, what's values doing? Iris data, iris is data. So I have X. Here I'm selecting these two features. All right, I notice. I convert them to a NumPy array. Why do I need these two features? Because this is the way how this what's the name? Example is represented in the book. So just a second, please. Just a second. Okay. So values is actually turning. Yeah, I was wondering why it turns this, how it turns this into a NumPy array. It does it using the values property. What else do I have here? What else do I have here? Oh, okay, so this creates a target array, and this target array will be a binary. It will only have two properties. It's only gonna have true. I have all of this data. It's only gonna have true if the target is equal to 2, which is, I assume, Iris Virginica. The comment says it. Otherwise, it will show false. Why do we need this? Because linear SVC. I think I'm gonna explain it. I'm gonna explain both the standard scalar and the linear SVC to myself to understand this better. But okay, so this is gonna be a binary array, target array. Then make pipeline. I create a pipeline. It starts with a standard scalar, which is gonna standardize the data. Then with the linear SVC, which is gonna train a linear SVM classifier. So why do we need one and then another? That's also something that I need to know better. So I'm just gonna write this. These are the questions I need the answers to. Why do we run standard scalar and then linear SVC. All right. Here I fit it. This will train the entire pipeline onto data. All right. And we do this because we want to separate the ones that we target from the others. Behind the scenes, scalar is gonna compute a mean, a standard deviation is gonna transform X, SVM is gonna fit a hyperplane that separates the two classes. Basically, wait. I mean, I already did this multiple times. But what happens here is, let's say these are the Virginicas. Let's say these are the other ones. I have no idea if this is the right data. I'm just explaining this. So we're gonna draw a line or a hyperplane that's gonna divide these two. Oh no, that's gonna divide these two. I need to now return my tablet. Sorry. Why is it so small? Okay. All right, I think this is good. Okay, so let's start with the standard scalar because I want to understand how it works in Scikit. I want to what it does behind. I want to know what it does behind the scenes. So it's easier for me. I mean, it's not needed, I think, but at one point, I might get a job in the industry. I might switch jobs and I might get a machine learning data science, whatever adjacent it is, a job. And I think things like this are important. So what's a standard scalar? Where are you? No, it's here. Standard scalar. All right. It's a data pre-processing tool. It's standardized. Standardizes your features, our features. What does it mean? It means that in the end, the goal is to have a mean of 0 and the standard deviation of 1. What does it mean? No idea. Let's find out. Okay, this is good because it ensures that all features are on the same scale. Like even with the huge amount of holes I have in my understanding of this, I can see why this would be useful. We have the same scale for all of our data. It's simpler to produce results. It's simple to predict, to train data and to predict new data on it. Let's say, okay. What if I have, for example, right. If I have, for example, height of a person and steps per day, and if I have here 160, 170, 180, 190, and if I have here 1,000, 3,000, 6,000, 9,000. Now, an unscaled model, in this case, might think that steps are more important just because they are bigger. Doesn't mean that steps are really more meaningful. Okay, so let's do another example here on standard deviation. Let's say I create a numpy array. This is a numpy array, and it contains 1.0, it contains 10.0, or 1 and 10. Why am I saying 0.0? 2 and 20, and then 3 and 30. All right. Let's say this is our data set. This represents here the first row, the second row, and the third row. Now, the standard scaler, what it does, it's gonna compute the mean for each column. So for this dude right here, we are producing the mean. What is the mean? It's the average of all the values. Why am I writing the decimals when they are, doesn't matter. Divided by 3, it's gonna be 6 divided by 3, it's gonna be 2, right? This is for the first column. Now the second one is gonna have 10 plus 20 plus 30 divided by 3, and it's gonna be 20. All right, so I computed the mean for each column. Now I should compute the standard deviation for each column. And how does this work now? How does this work now? Wait, let me find the formula for standard deviation. Google. I usually use tchdy for these kinds of example, but formula for standard. There you are. There you are. There you are. How to calculate the standard deviation? So it's the sum of. Is this the mean? This is the value minus the mean. I divide it by the total number of items. Wait, do I have another image? Do I have another image? Okay. The population mean. Total number for. Why the fuck do I have two derivation formulas here? What's the difference between a population deviation formula and a sample deviation formula? Fuck. Okay. 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 Let's run with it. Let's run with it. Oh, I forgot. I didn't actually. So it's gonna be a square root of what? The mean is 2. So each of these guys, I'm gonna divide 1 minus 2 squared plus 2 minus 2 squared plus 3 minus 2 squared. I could also do the inverse subtraction because they are squared, they will be positive in the end. I divide it by 3. So what do I have here? I have a square root of 1 squared plus 0 plus 1 squared. It's gonna be 2/3, and the square root of 2/3 is of 2/3 of 2/3 is, I don't know, square root of 2/3. All right, it's around, my friend ChatGPT just told me, it's around 0.1865. Hello for anyone who just joined. I'm simplifying the standard scaler, which is this method that scikit-learn preprocessor uses and provides to us, just to understand how it works behind the scenes. I think it's really important. Yeah, by the way, I'm also a beginner when it comes to machine learning, so learning all the basics is, in my opinion, pretty useful. I assume, because look at this. This is 2, this is 20, so I assume the standard deviation of the other of the second column will just be this on a scale to 10. on a new scale. So I'm gonna write the same thing, and it's gonna be the same thing. It's gonna be 10 minus 20 squared plus 20 minus 20 blah 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 plus 30 minus 20. I divide by 3, and yeah, it's 8.165. All right. Now I have here, this is the mean, and these are the means, and these are the standard derivations. Now I need to apply the standardization formula, which is actually gonna put all of our data that might be widely consistent and in different values in whatever range we want. I think in this case we want a range between 0 and 1. A range between 0 and 1. All right. And the standardization formula, how does the standardization formula works? It's x prim is equal to the value minus the mean, we calculated it right here, over the standard deviation. And then the first case, we have the x of 1, the x of 1, what's the mean? 2, what's the standard deviation? 0.8165. And the value that the new value that we will work with is 1.22. I'm gonna do the same thing for the second guy, 2 minus 2 over 0.18650, right? Yeah, I'm dividing by, and the third one, 3 minus 2 over 0.8165. Okay, my value x minus the mean divided by the standard deviation is gonna be 122. 122. So this is my first column, and this is my first column standardized or transform. Now the second one, now look at this, it's 10 minus 20 divided by, okay, this is the first one for column B. These were all for column A. I'm sorry. Okay, so these were all, this is the column A. Now I'm working here with the column B. 10 minus 20 divided by 8165, because this is the new standard deviation, is going to be 10, and the value in the total will be the same as this one. So these two values are basically identical. And B2 is the same thing, it's going to be 20 minus 20 over 5, it's 0. B3 is 30 minus 20, 81, blah, blah, blah. It's 0. So the new transform data will look like this. Minus 122. Minus 122 is the same data, only scaled. 0, 0, and then 122, 122. Now both features have the same mean. Now both features have the same standard deviation. I'm an idiot. When I drew the range, I did it from, no, I did from 0 to 1. I'm supposed to do it. I'm supposed to understand it like we have a 0, which is the mean, and then I have a standard deviation of 1 and minus 1. But still, no, have I understood something incorrectly? And then what we do? Because now they're on the same scale. I have the data that's on the same scale. But what do I do now with this data? What do I do now with this data? All right. There's also this. So once we call fit transform, once we call fit without transform, we compute the mean and standard deviation for each feature, and we store them internally. And then because fit and transform are two different methods now, and when I use transform, I use the stored values to apply to the standardization formula. So I have the original features. Feature A is gonna be 1, 2, 3. 1, 2, 3. Feature B is gonna be 10, 20, 30, and then the standardized features are minus 1, 22, 0, 0, and 1, 22 in the positive value. Okay, now this was the standard scaler. Let's also see how linear SVC works. Simply a simplified version behind the scenes. I need a new page here, and I need a new color. Let's use this yellow one. All right. So what is linear SVC? It says it's a linear support vector classification from scikit-learn. Wait, and the name of this chapter is support vector. No, it's support vector machines. I deleted this import. I didn't want to do this. Not my intention. Linear SVC. What's linear SVC? All right. So it's a classifier. It's wait here. It's a classifier that tries to draw the best straight line or hyperplane that separates two classes of data points. We also have, yeah, that's what I wanted to ask, because we also have SVC kernel linear. I could swear I saw it in the code before, and I was wondering how it works and what it does. But now I get it. So it's a different method basically. It's better, it says here, it's faster and better suited for large scale data sets because it uses a different optimization technique under the hood called liblinear. Okay, no idea what it does. Okay, so let's see I have this. Let's say I have this. I have some data. I mean, I already went through this, but repetition is the source of knowledge or something. I have two classes. I have blues, and let's say I have reds here. So I want to draw a line in 2D, or I don't know if I'm having if I'm doing this in the higher dimensions, maybe I need a plane that separates them. But I don't want any line. I want a line that has the biggest amount of margin, the one that is as far away possible. I mean, these are not three lines, these are just, that's as far away as possible for both. I also drew this incorrectly, but okay, it's theoretically as far away as possible from the closest point in both classes. And this is called the maximum margin hyperplane. The maximum margin hyperplane. So what's the idea behind this? What's the idea behind this? Just a second, let me... For some reason my internet's slow. Let me just do a speed test check. Okay. Okay, so it's not ISP's fault. Okay, the model tries to find a hyperplane, a line that has the following form. Weight 0, feature 0 plus weight 1, feature 1 plus weight n, feature n, plus the bias should be 0. Okay, so these are the weights, and they should be learned from training. This is the bias or the intercept, and these are the input features. The x's are the input features. And for prediction, it uses what? Y prim. What's this? No, this is not it. It's something else. But okay, let's do an example. Okay. Let's say I have two values. I have the inputs that look like this. This is an umpire array. It has 1, 2, then it has 2, 3, then it has 3, 4, then it has 4, 5. No. It has 2, 3. I just saw 1, 2, and 2, 3, and I thought they all have like a natural progression. They don't. The next one is 3, 3. The other one is 6, 5. The next one is 7, 7, 8. What's the other one? 8, 8. So this is the last one. And then I have Y, which is again an umpire array, and it has 1, 2, 3, 4, 5, 6. So it has 0, 0, 0, 1, 1, 1. Okay. Okay, asshole, let's see. The first 3 points, bam, are class 0. The second last 3 points are class 1. Now we need to train the model here. And I can train the model by calling the linear SVC method with a C of 1, whatever C is. Random, this is supposed to be an R, random state 0. And then I say model fit on X and Y on the inputs and the targets and the labels here. Okay, so what happens under the hood? Okay, so it's gonna find the weights vector and the bias. And the weights vector that maximizes margin. Maximizes the margin. What does this mean? How does linear SVC work under the hood? Man, Google is so fucking broken. Google is so fucking broken. Is this... I think that... The problem with this documentation is that it's too dense and I'm too stupid at this point to understand. Okay, in-depth explanation on Kaggle, whatever this page is. I know this. A hyperplane is a decision boundary which separates between given sets of data, okay. Support vectors. Who wrote this? And then we have the margin, and then it's under the hood. Yeah, the same thing as I wrote. You create a pipeline. Okay, this snippet picks properties differently that we did. It doesn't matter. It also picks the iris virginica. It creates a binary label array differently than we did, which is again no problem. I create a standard scalar. I just understood what a standard scalar is. And then I create a pipeline. And this one is labeled. For some reason, I feel that this dude here did this a lot better than the guys who wrote this notebook here. All right. But how it works under the hood, man, I don't care about this big picture. How it works? How is the math work? Ah, right. Here is something, even though I won't understand anything, but let's see. This is the line. This is the hyperplane, I assume. I know too little about this to properly understand this. I know too little about coordinate systems and way vectors are drawn on the linear space. I have no idea. I mean, I know a little, but not enough. Wait. Okay, okay. I'm thinking. Oh, okay. Wait. So what's our goal? We want to find a hyperplane. Now my second question is, what the fuck is a hyperplane? So I'm gonna put a question mark here. So a hyperplane that best separates the two classes. Okay. And I need to separate it with the largest possible margin and no misclassification. Let's, instead of using this example right here, which I spend a lot of time writing, let's do another one. Let's do another one. I have x1. I have 1, 2, 3, 1, 2, 2, 3. I have x2, 1, 1, 2, 0, 1, and I have y -1, -1, +1, +1. Now let's plot these. Let's plot these. Let's plot these. So this is x1. This is x2. What do I have here? 1, 2, and 3. 1, 2, and 3. I won't use 3, but okay. What's the first one? 1, 1. Am I even doing this correctly? Wait. Yeah, I understand. So first one is 1, 1. Okay. The first one is 1, 1. The second one is 2, 2. Bum, 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 bum. Bum, 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 bum. This is the second one. The third one is 2, 0. It's here. And the next one is 3, 1. Okay, so this has a -1, this has a -1, this has a 1, this has a 1. So what do I need to do? I need to... Wait, have I done something stupid and idiotic here? I have 1, 1, I have 2, 2. I have 2, 0. This is supposed to be a 2, 0. It's not a 1, 0. All right, I made a mistake. This is 2, 0, not the other one. And now I need to create a plane through this. So I want to minimize the error. I want to make the weights as small as possible while still ensuring that the points are correctly classified. There's a formula that I'm just looking at. It's quite a big one. Okay, let's assume a solution here. Let's say I have, let's say I have the weights are gonna be 1 and -1. And the bias is a 0. Let's say we have this. So what's the decision boundary here? What's the decision boundary? Just a second. what's a hyperplane? Hyperplane. A hyperplane is like a boundary or a divider in space. In 2D, a hyperplane is just a line. In 3D, a hyperplane is a flat plane. In higher dimensions, we can't visualize it, but mathematically the same idea, a flat surface that divides space. Okay, but what is... Because here it says, I need to calculate something called a decision boundary. What the fuck is a decision boundary? The decision boundary. Machine learning. Why is everyone explaining this on a higher level? Why does anyone know the basics of it? The math, whatever it needs. Wait. A hyperplane for a linear classifier, the decision boundary is described as. Yeah. I get it. I get it. I'm not as stupid as I should be. So basically, the decision boundary is the first weight, x plus the second weight, x1 plus b, it's equal to 0. And if I have values here, if I have values, wait, let me go back. If I have values here, if the weight is 1 and minus 1, so I'm gonna have x0 minus x1, the bias is 0, it's gonna be 0. So x0 is gonna be x1. The first x is gonna, the first feature is gonna be the same as the second one. And then after after finding the decision boundary, I need to compute the decision function for each point. I need to compute the decision function for each point. So it's y, the weight vector, times x plus b. What's the decision function? What's the decision function? Wait, let me find decision function. Decision function is a method present in classifiers, classifier class of scikit-learn machine learning, blah 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 blah. Where's the method? Where's the decision function, brother? Is this no? How to compute the decision function for each point? How to compute the decision function for each point? But this is not it. This is not it. Basically, the guide that I'm following says, okay, please compute the decision function. But the problem is that, wait. I love it. I love it. It's locked behind a paywall. I love it. It's not even a paywall. It's a sign up or some shit. What is a decision function? What is a decision function? How to calculate a decision function? This is not it. Wait. What is a decision function? I'm asking tchdy. I think they might give me some. A decision function is a formula used by a model to decide which side of the boundary. Wait, let me do this. Which side of the boundary does this data point fall on and by how much? It gives a score. It's not a class label. It tells us how confidently a sample belongs to one class or another. Okay, I'm using a linear classifier, so the decision function for a finally it's here. A decision function for a binary class for a linear classifier. The decision function is the weight vector times x plus b. I'm an idiot. Oh man, I'm such an idiot. I just realized what. Okay, where's the example? Okay, here. We have the weights and we have the bias. So what I do here, because the formula looks like this. Maybe I am an idiot. Wait, the first point is 1, 1, right? 1, 1, yeah, that's the first point. So what am I doing here? I'm multiplying 1, because I'm multiplying two vectors. I'm multiplying this one from the weights with the one which is here. 1 times 1, 1 times 1. Then plus the second one is minus 1 times 1 plus the bias is 0. So it's 1 minus. Could it be 0? Is the value 0? Is the value 0? It is 0. It is 0. The guide also says it's a 0, but what does this mean? I got a 0 here. What does this mean? All right, it's 0. I got the correct value, but what does this mean? Okay. So once I calculate the first point, and this is the first point that I calculated. So I have a positive score. All right, so if I have a positive score, is this a positive value? It should be a positive value. I put it in class 1. If I have a negative score, I put it in class 0 or minus 1. So if the value of this is greater than 0, then this is a class 1. Otherwise, it's a class minus 1. All right, so 0 is on the boundary. Let's see. Let's say that 0 is on the boundary. Let's do the same thing for the other point. The other point is, if you look here, it's 2 and 2. I'm going to do the same thing for the other point. So what I'm doing, I'm multiplying the weight. The weight is 1. By 2, it's going to be 2 times 1. It's going to be plus, but the weight here is negative. It's going to be 2 minus 2 times minus 1 by 0, so I'm putting it to be 0. So it's going to be 2 minus 2. It's 0. What? F of x is 2 minus 2. So it's 0 again. What does it mean? It's still on the boundary, right? I have no idea how this works. I have no idea how this works. Is there a YouTube video? YouTube. How to calculate a decision function.
Okay, in this presentation we're going to look at decision theory. So here we have a loss function under a decision problem, and we have 4 decisions and 3 scenarios. D1, D2, D3, those are the 4 decisions we can make, and we have 3 theta scenarios, theta 1, theta 2, theta 3. And what we have in the table is a loss associated with each combination of the D and theta. Okay, so which of the decisions can be discounted immediately and why? This is the first question we're asked. So essentially what we're doing is looking at each row, okay, and seeing if any of them are always worse than any of the others. So what we're going to do here, just to sort of speed things up, we'll compare D2 and D3. Okay, so 10 is worse than 7, 13 is no better than 13, and 17 is worse than 10. Okay, so in this case, what we can say is that D2 can be eliminated since it is dominated by D3. That is to say that under all circumstances, the loss from D2 is greater than or equal to D3. Okay, so we'll never pick D2 because D3 is better than it, or at least equal to it in every circumstance, apart from theta 2 where they're the same. But other than that, it's worse. Okay, so we're left with D1, D3, and D4. And I'm going to be frank with you, there's not really much you can do beyond what I've just given you there. But you can have a look anyway, just to sort of see what you think. Okay, now the second thing is, explain what is meant by the minimax criterion and determine the minimax. 17. This row here.
What? There's nothing here. Sorry. Why am I stuck here? Why am I stuck here? This is so stupid. This is so stupid. Okay, let's do this again. Let's do this again. So a linear SVC looks for what? What is this? So I want to find a solution to where's the function. So it's f of x, and it's again weight 0 x0 plus weight 1 x1 plus b. I want to find this, but I want to find it if y is plus 1. I want f of x to be greater or equal than plus 1. But if y is minus 1, I want f of x to be less than minus 1. This creates a margin of 1 around the decision boundary. And I want to minimize the error. The error is 1/2 weight 1 squared plus weight 2 squared. Okay, this is the squared length of the weight vector. It encourages a large margin. And every point needs to be on the correct side of the margin. So if I plug my points now, again I'm plugging them, -1. Why -1? Because y is -1 here. And this is for point 1 and 1. Wait, let me do the right. -1. So 1 and 1. -1. My first weight is gonna be weight 1 multiplied by 1 plus weight 2 multiplied by 1 plus b. It should be greater and equal than 1. So minus weight 1 plus weight 2 plus b should be greater or equal than 1, which means that weight 1 plus weight 2 plus b should be less or equal to 1, less or equal than -1. This is the first constraint. Then I have the second constraint and the third constraint. Okay. A lot of math here. So this is a decision function. Basically here I'm gonna get a value on how confident the algorithm is that a certain point fits the data. What do I have here? Neither of these look like they should. Let's go back to the basics. Wait. Let's go back to the basics. Bum. Where's my tablet? Where's my tablet? It's here. I want to move it. I want to increase it quite a bit. And then I want to move it here to the middle of my screen. Because I really need to drill this into my head now. Okay. Okay. Let's go back to the concept of linear regression here. Let's say I have a couple of points that roughly look like they are forming a line. Like this, 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 and let's say this. These are my points. So the goal of linear regression, this is linear regression. The goal of linear regression is to draw the line. Just a second. The goal to draw the line that passes as close to these points as possible. Let's say it's this line, even though I learned something cool now with these nodes. If I write a line and it's not as straight as it should be, I just hold it at the end and it creates a straight line, which is amazing. Which is really great. Alright. The goal of linear regression is to draw the line that passes as close to these points as possible. Okay. What line? How would I draw it? Let's say I want to build a road that goes through these points. These points are houses and I want to build a road. The road should be as close to these points as possible. How should I do this? How would these lines look like? Okay, so what does this mean? How am I drawing this line? How to find such a line? How to create it? What does it mean that these lines, that these points should form a line? So this is basically linear regression. So if I go back here, where's my code? It's here. And if I do one thing, just a second. Just a second. Let me download another data set. Oops, I don't need this anymore. I need to download another data set. Need to download another data set. All right, maybe not now, but let's keep it in mind for future. Where's my tablet? It's here. Again, let's say I have a table, and here we have only the number of rooms, and here we have the price, and I have 1, 2, 3, 4, 5, 6, 7, and here I have 150, 200, 250. This one is an X. We need to find this one. Then I have 350, then I have 400, then I have 450. So what price would we give to the house for based on the information of this table? Like it's 300, right? It's obviously 300. It's the same guess I would do, because there's a pattern here. We increase this by 50 from each increasing house. Because every time I add another room here, I have $50 is added to the price of the house. And basically, the price of the house is a combination of what? A base price of 100 and an extra price of 50 for each of the rooms. So I can have something like this. A formula that says price is 100 plus 50 multiplied by the number of rooms. So this is a model, and we have a formula, and it gives us a prediction of the price of the house based on the feature that we have, and the only feature we have is the number of rooms. This feature here is the only feature we have currently. And the price per room is called the weight of this feature. So 50 here is the weight of this feature. The base price, which is the 100, is the bias. Now I finally understand what weights and biases are. I mean, this is a really simplistic way of understanding this. Because I need to create a model, I need to create a formula, a model that represents a formula, or a formula that represents a model. Okay, so I have what? I have features. Features. So the features of a data point are the properties we use to make our prediction. The only feature here is the number of rooms. But we can have other features as well. What else? What else do I have? What else do I have? Oh, I need to get some water. I'm just gonna write. Be right back. 5 minutes. I'm sorry. I'm gonna try. Can I pause the stream? No, I can only stop streaming. I'm gonna be back as soon as I can. I'm sorry. Here I am. Mic check, mic check. Mic check. Okay, seems like I'm live again. Just remove this. I had to. I was talking too much. My mouth was getting dry. I also wanted just to get some fresh air before I continue. So, what am I talking about here? What am I talking about? Features. All right. What else do I have? I have labels. Labels are the targets that we are trying to predict from the feature. In our case, these are the labels. Then I have a model. A model is a rule or a formula. It predicts a label from the features. So in our case, the model is the equation we found for the price. Then I have the prediction. The prediction is the output of the model. If the model says, okay, if the house with 4 rooms costs $300, the prediction is $300. Then I have weights. So in the formula corresponding to the model, each feature is multiplied by a corresponding factor. These factors are the weights. The only feature I have currently is, where's my stupid formula? Here. This is the weight, the only weight I have currently. And also I have bias. Bias is a constant. The constant is not attached to any of the features. And this constant is called the bias. And in this model, the bias is 100. And it corresponds to the base price of the house. Now the question is, how this formula here, how can we come up with this formula? How can we find out what the bias, and the weights are? Okay. How do I find this? So let's do another example here. Let's say I have, let me just draw a line here. I have number of rooms and I have the price. And this time I'm gonna have something different. I'm gonna have 1, 2, 3, 4, 5, 6, and 7. The price is 155, 197, 244. For the house with 4 rooms, I have nothing. For this one, I have 356. I have 407, and I have 448. All right. Now, this one is similar to the other one, but this time we can't find a simple formula that easily. I have here 1, 2, 3. I fucked up. 4, 5. I fucked up. I need a bigger line. 5. Will this be enough? Hopefully. 6, 7. And here I have what? 100, 200, 300, 400. I need a bigger line above here as well. I must be kidding me. 400. And here I have 500. Okay. One, it's 155. It's here somewhere. The second one is almost 200. It's here somewhere. The third one is 254. Let's say it's here. The fourth one I don't have. The fifth one is 356. Let's say it's here somewhere. The sixth is 407. It's slightly above 400. Let's say it's this one. And the seventh one is 448. It's almost 4. Let's say, let's split the difference between 400 and 500. Okay, this is the plot of the points in the coordinate system, in which the horizontal axis represents the number of room and the vertical represents the price of the house. Okay, so in this case, it's similar, but the difference is we have an error. And let's write the formula to look like this. So the price is what? Is 100 plus 50. Number of rooms plus, let's say we have an error here. And we have an error here. So I need to predict prices. I need to predict prices, and I need to use this equation. All right, so if I look at the plot again, so what happens if I look at all the points in which the vertical coordinate, so y, is 100 plus 50 times the horizontal coordinate. Okay, so I have 100. It's 1 times 50, 200, it's 2 times 50, 300 is, I mean, the price is 300. It's 3 times 3 is the number of rooms, and 500 is our weights. So it's here, and basically I can interpolate all the other points with this. It's, what's this? This is 4, blah, blah, blah. So I create a line. So what's a line? The line has a slope of 50 and it has a y-intercept of 100. So what do these points mean? So what is a slope? Let me just draw this line. Hopefully I will draw this line correctly. Ah, I messed the lines. I messed the lines. Because if I wanted to do the other ones, it should be 150, 200 on every 50, not on every. I messed this up a bit. Wait. So for 100, I should have 0. Oh, I made a fucking stupid mistake. How can I remove these red points now? Wait, maybe I can. Oh, okay, I can just go backwards. This is good. I'll just write these points better now. But I can't do this here. Okay, well, let's do this again now. So for 100 I have 0, right? For 150 I have 1. For 200 I have 2. 350 is 3. 4 is gonna be 300. 5 is gonna be 350. And this is basically the line. It goes something like this. So what this all means? What is slope? The slope of a line is a measure of how steep it is. I calculated by how many units it goes up divided by how many units it goes to the right. And this ratio, because this is a straight line, right? This ratio should be constant over the whole line, right? Corresponding. So what we know about this line is that it tells us how much we expect the value of the label to go up when we increase the value of the feature by 1 unit. If the line is horizontal, the slope is 0. And if the line goes down, like in our case, no, in our case it goes up. It's positive, but if the line goes down, the slope is negative. What is the y-intercept? The y-intercept of a line is the height at which the line crosses the vertical axis. Y-axis. It's the bias. It tells us what the label would be in a data point where all the features are precisely 0. All right. So what the label would be if the features were 0. Okay. Because the hypothetical price of a hypothetical house with 0 rooms would be 100. It's the base price. And what is a linear equation? Let me close this VS Code in the background. I don't need it anymore. The linear equation is the equation of a line. And I can draw this line by 2 parameters, the slope and the y-intercept. So if the slope is m and the y-intercept is b, then the equation of the line, and I need only 2 properties, is y is equal to m, which is the slope, x plus b. And the line is formed by all the points x and y on the coordinate system that satisfy this equation. In the machine learning model, x is the feature and y is the prediction of the label. And the weight of the bias are m and b. Now, because where's the formula? The formula is here. It's going to be 100. That's the bias. And m, or the slope, will be 50. what does it mean when the slope is 50? It means that the price of the house will go up by 50. And when we say that the y-intercept is 100, this means that the estimate for the price of a house with 0 rooms would be 100, as I said. Okay, so I have this line here, and I picked this line with these values because it's close to the points. They might be a better one, but this one is decently good. As opposed to, I don't know, let's say this line that isn't going close to the properties at all. So how can I build a road that's as close as possible to these points? Let's say this is as close as we can get. We can optimize this later, but what do we do now when a new house comes to the market? So now I say, okay, y is the price. I'm gonna say the price is the slope 50, not 500. 50 times 4 plus 100. Let's say the price is $300. So our model predicts that the house will cost $300, and we can see it graphically here. It would be, no, it's the blue one. It would be, let's say, somewhere here. All right, what if we have more variables? I'm gonna do this later. I just need to take another quick break. Let me just stretch my legs, and I'm gonna be here for some Unity. Be right back. 5 minutes. Okay, I'm live again. I'm live again. Let me delete this. Let me remove this. Bum 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 bum. And let me run Unity. Unity hub. I need to accept this every time, right? Okay, okay, okay. Okay, so I have these prefab objects. If I click on this, this should be a prefab, right? Prefab, yes. So I have the original prefab objects and I have all the copies. So prefabs are in blue. That means that an object is an instance of a prefab. And it was created based on a prefab. Okay, so what can I do? What can I do now is if I click the blue objects, and I can see the original prefab objects that created these other objects. But I have also these copies here. They look the same, but they are not instances of the prefab. And what if I click it here? Do I have a prefab here? Prefab, replace, enemy object. Is this it? Is that what? That's it. Okay. Okay, interesting. All right. So I have a prefab. I have an instance of the prefab. So we have options. We have bindings that help us to revert and apply changes between prefab and the instance. So if I take the prefab, this is the prefab. How can I change it? If I take the prefab, and I make some modifications to the prefab, these changes will be automatically applied to all the instances across the scenes in the project. All right. Okay, so I clicked the prefab, but I didn't want to do this, man. How can I go back to the scene now? Oh, okay. So I click the prefab object, and I can add a component to it. I can add rigid body, so that because these are enemies, they can fall. And now if I click on every one of these, they should have a rigid body. Yeah, and if I run this, they should be falling now. Cool. Okay. Alright, but individually I can override prefabs, I assume. I can override them. All right. How can I scale this? 0.95, 0.25, 0.88, 50, let's say 60. All right, so I have overridden this instance, and because overrides have precedence over prefab, this one will keep its own version of the scale. Okay. Okay, how can I see all the overrides? What if I override this guy as well? What if I say that this guy will be 1.5 the size of the prefab? How can I see all the overrides? So if I select instance, if I select the instance, and where are the overrides? Where are the overrides, brother? Overrides. Ah, right, so here are the overrides. I can revert all or I can apply all. Okay. But I can also, I can also apply to all. Okay. Oh, guys, I need to go. I apologize. I'm gonna see you some other time.